All right, well, I trust you did well on your exam in our last lesson. Students in here did pretty well. A few things here and there we had to address, but overall a good job on chapters 13 through 18. We go now into the final quarter of the school year, and if you're keeping track, there are obviously a lot more chapters than 6. We're doing about 6 chapters a quarter, and we've got more than that to cover, and you've got senior trip you're going to be missing some time on. So what I'm kind of going to do this quarter is we're going to hit these next couple of chapters pretty hard, 19 and 20. And then from there, I'm going to kind of skip around and hit what I think are the highlights of the rest of the book. So we'll have to skip a little bit as we go through this fourth quarter. But I do want to hit 19 and 20 pretty well here as we study light in a little more depth. We looked at sound in plenty of depth. We just looked at the tip of the iceberg, so to speak, on light, really just what is light. And want to study light in a little bit more depth in a section of the class we'll call optics. Optics. Optics refers to the study of light. That was also the title of a couple of different books that have been written on light, including the book I referenced this earlier, Al-Hasan or Ibn however you say his last name. Anyway, that guy, the Arab guy, who first proposed that light was actually, comes from, is reflected off of other objects that we see. Optics. I believe Newton wrote a book on optics as well. Of course, that was his corpuscles and stuff, but still. Optics, the study of light. We are going to begin looking at this study with what we call geometric optics. Geometric optics. There's 2 ways to look at light in a sense, and we're going to approach it, first of all, from the geometric optics viewpoint. Geometric optics treats light as an infinite number of individual parallel rays. Geometric optics treats light as an infinite number of individual parallel rays. So as the light comes from this source, now we understand light is coming outward in all directions from this, right? If this is the only light in the room, it will still in some ways illuminate something in the back of the room. But to any object, we could assume there are an infinite number of infinitely thin parallel rays. So there's all these parallel light rays coming down and they're all hitting me, hence I am now illuminated. I am bright and visible because light is coming down to me, but we're going to view it as infinite number of infinitely thin parallel rays. Now, with these rays, then, as they travel through the air or as they reach a boundary, several different things could happen. It is possible that as the light is shining down through the air could actually absorb some of these rays. It's unlikely, but it's possible, I suppose. Maybe if light is going through maybe a piece of glass, or it's going through water or something, or some liquid, perhaps some of the light could be absorbed by the medium. Certainly, though, when light strikes a surface, light can be absorbed by that medium, correct? That's that radiation energy that causes the medium to become warmer. So light can be absorbed then. Light rays, if we will, can be absorbed. Certainly by the second medium that they hit, but in some rare instances be absorbed by the medium through which they initially travel. Light rays can be transmitted. Light rays can be transmitted by a medium. Certainly through the air, the light rays as they come down from the light, they are transmitted right through the air right to me. All right, so light rays can be transmitted. They could strike a surface that happens to be clear, right? They strike the surface of the water bottle and they go into the water bottle. They're transmitted into the water. Rather, they're transmitted into the water as well. So light rays can be absorbed, they can be transmitted, they can be scattered. We said this will happen with a translucent object. They'll be scattered as they're transmitted. It's also possible that light rays could be scattered as they're passing through. For instance, you ever noticed sometimes when the sun peeks out behind the clouds, it's almost like you can see sun's rays coming up? Well, what it is there's enough humidity or moisture in the air that the little water molecules, as the light rays hit them, you can actually see the light scattering as it hits each of these, water molecules in the air. And so you kind of see these beams of light. On a clear day, do you see anything like that? No, the light just comes down. I did this when I was a kid. I don't know if you ever did this as well. Maybe noticed that when you grab a tissue, maybe the sunlight is beating down upon the tissue box. You pull out a tissue and there's this little cloud of dust that rises. Okay, I discovered if you rub the tissue, it makes lots of dust. I don't know if anyone's ever done that. And okay, you did. Okay. So I remember being a little kid and I was sitting there in my room as the sun was beating in the window nice and brightly and rubbing the tissue. And what you could see is as the light rays came down, as they hit the little particle of dust, you could actually see a really bright spot right there. More bright spots as the light rays were being scattered by the little particles, if you will. This happens, I think you might remember in physical science, maybe shining light through milk. You ever see how the light shines through milk? Well, that's because there's the little clumps in the colloid, right, of milk, or the little fat glumps that are evenly distributed, assuming it's homogenized, right? Talked about that earlier in the year. Well, as the light strikes those, you see that. We're going to be doing some demonstrations with light more in the next chapter than in this one, but we're going to be able to see, I use pine sol as a scattering agent. I put it into the liquid, so when I shine a beam of light into the liquid, you can see the beam forming. Well, if I just shine it through pure water, the beam goes right through. It's just transmitted. You don't see anything. But little molecules of the pine sol scatter, so you can actually see the beam form. Today we're going to do that with some haze, some professional haze, like a fogger machine, except it's in a can, and we're going to be able to see the beams of light. Maybe in like crime movies or whatever, you see the beams of light through and surrounding the priceless diamond, and the thieves are trying to find a way to get around all the beams. So they spray some fog in the room so you can see, okay, where's the laser beam, where's the invisible beam, stuff like that. Okay, so scattering is possible, but certainly when light strikes a surface, light can be reflected off of that surface as well. Light can be reflected off of a surface. And these are the primary two reactions or responses to light rays, if you will. As they strike a surface, they're either absorbed or they're reflected. We said all three of you have that navy blue hoodie on. Well, most of the light that strikes the hoodie is absorbed. A little bit of the blue light is reflected off. That's why we see navy blue. If you were wearing a bright blue hoodie, we see a bright blue cloth over there. And no, I couldn't get in the camera at this point, but that reflects a lot of blue light. It's a lighter blue color. And so reflection of light is what this chapter is primarily going to deal with. If you would write this term down in your notes then, reflectance. Something I more or less just alluded to and had alluded to before as well. Reflectance refers to the ratio of reflected light, to all incident light. The ratio of reflected light to all incident light expressed as a percent. The ratio of reflected light to all incident light expressed as a percent. I'm going to try to demonstrate this for you. I've got a couple of lasers here, and one of them is a red laser, and the other is a green laser. Now, just kind of by looking at it, which one appears to be brighter to you? The green. And they're actually roughly the same energy. These are both professional science grade lasers. The difference is the green has more energy in it, so it seems to reflect off better. Now, if we shine the green laser beam here, obviously it's striking a white surface. So we would expect all of the light to reflect off, or most all of the light to reflect off. So you pass here, you see as it goes to the gray, not a huge marginal difference. This comes to the green, not a huge difference as well. Right? Why? Because a green surface should reflect more green light. We see a pretty high ratio of reflected light here. With the red, also again, it's a shinier surface here, so we see the red beam reflected off. Michael, I need your help for this next thing, if you would, sir. We would expect something like black to absorb a lot more. So if you just hold this up there on next to the white there for me, just hold it up so there's a little bit of white and a little bit of black. And so we see here, obviously the red is reflected pretty well. We see it pretty clearly. Now, do you see how it seems to get dimmer right here? That's because black is going to absorb more, but you can still see the laser beam, correct? Light is still being reflected off of that substance, even though that black felt has a pretty low reflectance. It's not going to reflect a lot of light. It still reflects some. You can still see that red laser beam, just not nearly as bright. The green might be even more striking. We see the green really bright, radiant, almost blinding as it reflects off. If you come here, still see it pretty brightly, but it doesn't have that same brightness to it, if you will, because the black has absorbed some of the light. It could also be that the fibers of the cloth kind of allow the light to go around. Just a small card here, so we're going to hit the card with this. the same kind of demonstration here. Do you notice the fibers tended to have a more dramatic effect? You can still kind of see that radiance around the green beam, right? Even on the black card here, the red even seems to have a little bit of radiance about it. And that's it's a black piece of linen paper, if you will. And so the black absorbs a little bit of it, but did you notice the fibers tended to absorb more because the light was kind of allowed to go down in between the fibers. They actually have a new material they've come up with called Vanta Black. And what it is, it's a bunch of little, what are called nanotubes, tiny little tubes, billions of infinitely small tubes, infinitely short, infinitely small. But as the light hits it, instead of being reflected off, it kind of reflects around inside the tubes so that the light doesn't come back off. And it was pretty neat. I was watching a video. I'll post a link to it in here, and I'll show it at the end of the hour to you guys rather than interrupting class for a 16-second video. But you see the same kind of demonstration I just did with those substances. They just shine the laser beam. And as soon as the laser gets over the black, you see nothing. Nothing reflects off at all. Another material called Spectra Black. Is another material where it's kind of interesting. They show these 3 different black materials and they shine just a normal flashlight beam. And you see a little bit of white light reflected, a little bit, you see nothing, no impact at all. They come up with materials that have extremely low reflectance. Most black substances like those are still going to reflect off about 5 to 10% of the light that hits them. So for most materials we would come up with, 5 to 10% reflectance is going to be true for most black substances. They're going to absorb 90 to 95% of the light, but they'll reflect between 5 and 10%. Whereas white surfaces usually reflect upwards of 90% of the light that hits them. Now, a highly polished silver, especially pure molten silver, has a very, very high reflectance rate, even higher than that. But reflectance just refers to the percentage, if you will, of light that is reflected off. Again, some of the light all hits it. What percent of that light reflects off? If 9 out of 10 light rays, so to speak, reflect off, then we've got 90% reflectance. Now, with this reflection, though, we understand that just because light reflects off, for instance, light reflects off of Kendall's hoodie, right? Well, that means then that light that strikes Kendall's hoodie reflects back to me. Right? Hence I see Kendall's hoodie. Well, theoretically, light that reflects off of me reflects off of Kendall's hoodie. So I just straighten up my tie here. It doesn't work that way, does it? But it could work that way in front of a mirror, certainly. Right? I've got this polished, very chalk dusty faucet here. Now it's a little distorted here, but I suppose I could straighten the tie in this little faucet handle. Maybe you've done that in the car window before. Something like that. Just check to make sure, does the necklace look okay? Does my hair look okay? Is the tie straight? Even in the nicely, if it's not covered in pollen, which this time of year is hard here in Georgia, but even in the side of the car, right? Even if it's not a car window, just the side of the car, if it's nice and shiny, you can maybe see yourself, see your reflection. It's usually rather distorted, right? You might look kind of skinny or fat or short or tall, whatever. Kendall's like, I always look short, I don't know what he's talking about. But anyway, reflectance, there's 2 ways in which light reflects. Off of Kendall's hoodie, light does reflect off, but I can't see myself. Off of this white paper, light does reflect, but I can't necessarily see a clear image. But if I were to, let's see what Miss Morse has here in the desk drawer. Ah, yes, she has one of these. All right, so a hall pass. They're a nice bright orange. Do you see on the paper here, do you see how there's some orange shining on the paper? In fact, if I shine it this way, you can see it pretty clearly, can't you? You can almost kind of see where the logo is. Kind of right? Where it's a little bit grayer because not as much light's reflecting off. I'm not sure if I'll be able to catch this on camera or not, but you can just take a bright piece of paper and kind of hold it up to another white piece of paper, and you can see the light reflecting off. Light is definitely reflecting off. Light from the bright orange pass reflects off of this white notebook, because white reflects a lot of the light, but you don't really get a clear image. There's 2 ways in which light reflects off. The first type of reflection is called specular reflection. Specular reflection. You remember from English class, spec, spect, spick, to look or to see, right? One of your roots. Specular reflection refers to reflection for images that you can see. The word specular actually refers to image-like. The word specular actually means image-like. This is reflection that produces a clear image. Reflection that produces a clear image. If I take that same hall pass and I hold it up with a mirror this time, you can see a very clear image, right, of the hall pass. I wouldn't even need to show it to you to tell, but just for contrast. Now, it's the same thing basically happening as light rays hit the bright orange pass. They reflect off of the mirror to your eyes. I don't know, it's a plastic mirror. It's not a super fancy one. It's not glass or anything that would reflect super nice, but I'd say reflectance here is probably 85 to 90%. Oh, the white paper probably has 85 to 90% reflectance also. Why the difference in the reflection? Well, this produces what's called specular reflection, produces a clear image, and the reason is that the parallel rays, they hit the hall pass, okay, so here's the hall pass, and they reflect off of the hall pass, and they hit let me draw that a little bit better, and they hit the white piece of paper. Well, when they hit the white piece of paper, instead of staying parallel throughout like they would off the mirror, the paper, if you looked at the surface microscopically, you'd actually see there's all kinds of little bumps and ridges in the piece of paper. So when the light hits the bumps and ridges, the light rays go wherever they want. And so the light rays are kind of scattered around. But on the mirror, since it's a nice smooth surface, light rays come in parallel, they come off parallel, and they stay parallel, coming off. This is because parallel rays reflect parallel off smooth, that's the key, surfaces. And you say, well, my paper is smooth. See, I'm feeling it right now. It feels very smooth. Well, to the touch, yes, it's nice and smooth, but it's not a polished smooth, so to speak, right? And that's actually a good thing. If the paper were really super smooth, you know how yearbook pages are really super smooth? Okay, if you try to sign in them with a gel pen, what happens? Smears everywhere. Why? There's nowhere for the gel ink to kind of get down into the grooves and absorb into the paper. This kind of paper I could write with a gel pen, and it might take a second for the gel pen to absorb down in, but it absorbs down in just fine. Why? Because this paper is not super smooth, right? For instance, you know those labels that you peel and stick and that super smooth label side? Well, I was printing some CD labels years and years ago now, and I would print them, and I try to print 2 at a time because there's 2 labels on the page. And but if I printed 1 at a time, for instance, I might still have a little bit of residual printing that needed to print where I'd already peeled a label off. It was amazing, the toner from the laser printer would just slide right off of that really smooth. Well, that's because there's no little grooves for it to get down into. That's really smooth. This isn't. So the light rays, instead of staying parallel, they're kind of scattered. You still see orange, right? You still see light rays come down, they hit the paper, orange light is reflected off, and so you see orange light, but it's kind of scattered. The image of the little Crusader logo kind of goes all over the place, right? If I look at my own reflection here, paper in my hand, who's the fairest in the land? Anyway, so the light rays, for instance, they strike my nose, they hit the paper, and part of my nose goes there, part of my nose there, my nose goes all over the place, so I don't see a nose. Here, oh my, I see the nose, right? Light rays hit my nose, they reflect off the mirror back to my eye. I see what my nose looks like because all the light rays from my nose come right back together. They're not scattered around. Scattered around reflection is called diffuse reflection. Diffuse reflection. It would be just the opposite. No clear image is produced. Diffuse reflection has no clear image produced because light rays, when they strike an uneven surface, are reflected in various directions. Light rays don't stay parallel. Parallel rays, I should say, do not stay parallel anymore. So the ray from the top of my nose and the ray right below that and the ray right below that and the ray right below that, they all come in parallel. They hit a mirror, nice smooth mirror. They all reflect all together. So the top of my nose, the next part of the nose, the next part, they all come back to my eye together. Off the paper, they go in all different directions. So parallel rays do not reflect parallel off of uneven surfaces, so no clear image is produced. The word diffuse or diffuse has the idea to kind of dissipate, right? Like a diffuser, anyone have, moms maybe have diffusers in bathrooms or something where they've got the little essential oil or whatever, the little straw-looking thingies, and the oil kind of just diffuses into the air, and it smells good all throughout the room. That's kind of what's happening with your nose, a little of the nose all over the room, right? And it does because of an uneven surface. So the two types of reflection class that we have are, and which one does not produce a clear image? Diffuse. Which one does produce a clear image? What type of surface will have specular reflection? Smooth, and so therefore uneven surfaces produce diffuse reflection. You kind of see diagrams of that on page 278. I forgot to have you turn the page there. Page 278, you kind of see at a microscopic level what's happening with those light rays, so to speak. All right, next thing you know, it's laws of reflection. Laws of reflection. The first law of reflection is something we already have memorized. Just write it down. The angle of incidence equals the angle of reflection. First law of reflection says that the angle of incidence equals the angle of reflection. Angle of incidence equals the angle of reflection. Remember, these are both measured from the normal. So you might want to make that note. These angles are measured from the normal. Angle of incidence equals the angle of reflection. These angles are measured from the normal. Now, that's easy enough to show, right? If you have a nice smooth surface, if the light ray comes in and it strikes right here, okay, we put the normal here. Here's the angle of incidence, theta sub I, so the angle of reflection, theta sub R, has to be equal. But what if it hits an uneven surface, right? In the case of diffuse reflection, right? Let's suppose as the light ray's coming in, we've got this bumpy surface. This is maybe a little over-exaggerated, but let's just suppose a light ray comes in and it hits right here. Where's the normal? Well, we would have to assume at this point of contact, we would put a tangent plane. From geometry, we remember tangent means it's a line that touches, or in this case, a plane that touches at only one point. The way this curve is drawn, I'm guessing the tangent would be something like that, at that exact point. Well, in that case, we would put the normal to the tangent, the perpendicular to that tangent plane, so that this would be theta sub I. Theta sub R then would have to come in this way, and it would reflect back into one of the other surfaces, and then would reflect again, and so on and so forth. So for uneven surfaces, you may make this note. For uneven surfaces or even curved surfaces, the normal is perpendicular to a tangent plane. The normal is perpendicular to a tangent plane at the point of incidence. And we see a diagram of that as well on page 279 in your textbook. See that incident ray coming in on the curved surface. They drew a tangent plane, and then the normal is perpendicular to that. The second law of reflection is kind of a duh statement, right? But it bears mentioning, and that is that the angle of incidence, the angle of reflection, and the normal, the angle of incidence, theta sub I, the angle of reflection, theta sub R, and the normal, or the perpendicular, all lie in the same plane. The angle of incidence, the angle of reflection, and the normal all lie in the same plane. Angle of incidence, angle of reflection, and the normal all lie in the same plane. The book has their approximate sketch of this on page 279 as well. They show that if an angle, a laser beam comes in, for instance, at an angle, light ray comes in at an angle, not only is the angle of incidence equal to the angle of reflection, but the plane in which the ray comes in is the plane at which it goes out. It would not come in, for instance, at one plane and then shoot off into a separate plane altogether. I'm going to try to demonstrate this. I'm going to have Michael come help me here in just a second. If you would first though turn off the lights. And again, I'm not sure how well the camera is going to catch this, but we're going to try to catch this here. And so we're going to fill the air with a little bit of scattering agent, a little bit of fog. All All right, in hopes that you'll actually be able to see the laser beam here. Yes, you can see the laser beam shining through the air. And we can see then, and I'm making just a little bit more scattering agent directly over here. As the laser beam comes in, we see as I change the angle of incidence, yeah, Michael, don't get hit by this, we change the angle of reflection. Kind of hard to see, I'm afraid, on camera, so I apologize for that. Play around with your own laser beam, I guess. But I also want you to see that as I change, not just the angle, does the angle change, but as I change the plane, obviously the plane changes as well, correct? It always stays in the same plane. Now, Michael, I'm going to have you come over here, if you would, stand back here. And if I wanted to shine the laser beam at this angle here, let me shine it straight. It's non-toxic, so don't worry. All right. If I wanted the laser beam to hit the back wall, what would Michael have to do? That's the side wall. What if I wanted the back wall? That's the front wall. What about the back wall?
Back wall.
Okay, not hitting girls in the eyes, though. Right? We have to change the plane. Because the laser beam is always going to stay in that same plane. Now, if I change my position relative to it, I could redirect the laser beam, and I could probably still hit. I'm trying to get it on the side wall here. Easier said than done at that angle. All right? But do we see how the incident ray is always, that angle stays the same with respect to the normal, but also always stays in the same plane with each other? You see that? Do with the red beam as well, just because I like playing with lasers. Tomorrow we're going to get a chance to play with this a little bit more. So the red beam, again, I'm getting the incident beam, I'm getting really well. The reflected beam is harder to get to show up here, but I'm just kind of seeing it changing all throughout there. All right, questions on that? You guys get to see it. Well, again, we'll play around with that a little bit more tomorrow. If you'll turn the light back on, Michael. Again, if that didn't show up very well on YouTube, I am sorry. I'm feeling it probably wouldn't, but at least students in here got to see it. And again, if you're watching on YouTube and you happen to have a laser and a mirror that you can use, even if it's like a compact mirror or something, play around with that. And clock erasers to make chalk dust. People have done that before. I prefer the fog, which dissipates on its own eventually. Right now, there's a bit of a haze in the room. I suppose we couldn't know, because if we open windows, we get a whole separate haze. We get yellow haze coming in from out there with the pollen. All right, let's move on then. The mirror that we were using a moment ago is something we're pretty accustomed to seeing. It's a small mirror, but it's flat, right? Most mirrors we use on a regular basis are flat. In fact, if they're not flat, it makes weird things happen, right? You've seen maybe at, they have these mirrors in the play places at Chick-fil-A for the little kids. Audrey still goes in the play places at Chick-fil-A with the little kids. And that's okay, I guess. You're not a scary person, so I guess it's okay that you're in there, right? But they distort your image a little bit because they just change the shape of the mirror a little bit. In fact, I remember it was several years ago, Shark Tank, they had a product called the Skinny Mirror that was being advertised. And this mirror was one that the shape was just right, that when you stood in front of it, it kind of flattered your figure a little bit. So you looked really nice, even if you were like a fat lard. When you look in the mirror, you'd see yourself as skinny. They said, this is going to help promote self-esteem. So we wanted people to buy the Skinny Mirror, so when they see themselves as beautiful. Except you bought the Skinny Mirror, so you know it's lying to you. So do you really have high self-esteem when you look at it like, man, I look good? Oh yeah, it's the Skinny Mirror. Like, is anybody really going to buy that thing and then believe that they look like that? No. And what if you got it as a gift for someone? Like, you don't think they're going to notice, that looks different. What are they trying to say? Right? Like, that's no good either. And then what if you do really genuinely, like, you completely buy it and you tell yourself, this is how I really look. I really do look good. Well, now you're contributing to obesity. So no matter any way you slice it, it's a terrible product, terrible idea. The Sharks did not give it an investment. But anyway, most mirrors that we use are flat, perfectly flat. Most of them in the bathroom, maybe in your bedroom, you've got a mirror, something like that you can use. I want to talk next about mirror images from what are called plane mirrors or flat mirrors. The term is a plane mirror, though. So let's talk a little bit about these images that we see. Mirror images. And we're going to start by talking about plane mirrors because that's what we encounter most frequently. When you look in a mirror, hi Kendall, hi Audrey. Michael? If they could catch that on video, I don't know. I doubt it. But maybe they did. I don't know. You see Kendall? I'm just having fun. Wait, I think I almost got her. You're going to see different than the camera. I'm trying to do it from the camera's point of view. Wait, I almost got it. Ah. That's somebody. I can't tell who that is. That is Michael. I think I'm getting Michael. I don't know Michael. We've already seen. Hey, there's Kendall. No, because it's just a reflected image. We're not actually seeing Kendall. Ah, you see? Anyway. I digress. But what we see is everything's upright, first of all. That's the first thing to note. What we see is an upright image. Now you say, well, duh. Well, not necessarily. Y'all have played around with looking inside a spoon, right? We know that sometimes what you look at is upside down, right? We're going to talk about why in the next section. But with a plane mirror, that's never the case. Can you imagine how hard that would be if you walked in front of the mirror and everything is upside down? You're like, okay, put my hand up, hand goes down. Like, try to figure that out. That would be so annoying. So it's nice that plane mirror images are upright. The next thing's kind of interesting, though. Mirror images by a plane mirror are always what are called virtual images. Virtual images. Think about it. You have a mirror on the wall. You look in the mirror. Where do you appear to be in relation to the mirror? Behind it. Correct? The light rays you see seem like they're coming from behind the mirror. Obviously, as you step further away from the mirror, it appears to move further back behind the mirror as well, correct? Is the image actually back there? Are any light rays really back behind the mirror? No. But it feels like, it seems like the light rays are back behind the mirror. And because that's true, we get something called a virtual image. Your definition here would be any image that seems to be formed by light rays behind a mirror. An image formed by light rays that seem to be behind a mirror. Light's not really back there, but it seems like it is. Called a virtual image. So images are upright. They're not flipped upside down. That's not always the case with all mirrors. They're virtual. By the way, that's not always the case. There are some mirrors that actually reflect an image out in front of the mirror. So you're here, and the image is also out here, and there's the mirror. The image doesn't appear to be behind the mirror. It's actually still in front of the mirror. We're going to talk about those here in a little bit as well, or tomorrow, or actually 2 days from now, I guess. But virtual images appear to be behind the mirror. The image is unmagnified. If it's a truly plain mirror, the image is unmagnified. Now, this isn't always the case, right? You ladies know, you got the cosmetic mirrors, the counter at the mall, right? You walk past, and if you see anything, it's usually upside down, isn't it? But if you get close enough, it's like, man, there's my face. It's huge, right? It's like my nose was this big. Now it's this big, right? You played around with the mirror. Okay, but a truly plain mirror, right, is perfectly flat. It's completely unmagnified. What you see really is the size you are. Now, the further away you get, because of your distance, it appears smaller, right? But if you get right up close to that mirror, what you see is your actual size, right? Whatever, we won't go there. All right, so it's an unmagnified image. Again, that's not the case with all mirrors. Obviously, the cosmetic mirror, that's not the case. It does magnify. It makes things seem bigger. The next thing that's rather interesting is a mirror image in a plane mirror is always reversed. The plane mirror image is always reversed. You ever thought about this? You stand in front of a mirror and, okay, I raise my right hand. What does the object in the mirror do? Raises its left hand, correct? It's reversed. Your right hand, its left hand. Because it's mirroring what it sees, correct? Now, you could actually undo that reversal if you used a second mirror. I don't know if you ladies have ever done this. I do this because I cut my own hair. But I have the mirror behind me and I have another handheld mirror. And so when I move my right hand, the right side of the image is also moving. So I use a second mirror to do that. You can kind of get the same illusion. It's kind of students always freak out when they see this, but if you take two mirrors, obviously you set them in line with each other, you get that, you know, kind of infinite reflection nonsense going. I could see both mirrors in the mirrors. And but you kind of get the reflections bouncing back and forth. But if you just set mirrors at a right angle to each other, for instance, we'll see if we can get this effect to work. But we're going to start with Kendall because she's right down front. Kendall, I want you to kind of position your face, or you might even take the mirrors from me so that your nose is right on the crease. Okay, now close one eye. This eye, your right eye closed, if you look at your image over here, it's right eye closed as well. It's because there's a second reflection taking place. So you close your right eye, it closes its right eye. It's on the opposite side of you. If you can position your face, your nose is right in the middle, close one eye, and you'll see that over here it closes the same eye you did, so to speak. So a second, really it's not so much even two. Let me see if I can get that lined up there. Can you see it? All right. So right angle mirrors, really it's just an even number of reflections will undo the reversal. So if you want to jot that down, having two mirrors, really an even number of mirrors, even number of reflections will undo that reversal. Interesting though, where is the reversal taking place? Well, it's not really an x-axis reversal, is it? Right? It's not as though when I look into a mirror and I point this way, that the mirror points to the other side. The mirror points the same direction along the horizontal that I do, doesn't it? If I were to point up, the mirror would also point up, correct? What's different is, if you think about, and we haven't talked about three-dimensional graphing in pre-calculus yet, but you understand there's the x-axis, there's the y-axis, and then in three-dimensional graphing, there's an axis that comes off the chalkboard. It's called the z-axis. Now, when we draw it this way because to give the illusion, but it's actually coming off the chalkboard. That's where the reversal takes place, is along the z-axis. If I point at the mirror points back at me. We both match, we go opposite along the z-axis. So it's a z-axis reversal that you get from a plane mirror image. Kind of interesting that we get that. The last thing is, does a mirror reflect 100% of light that hits it? No. Nothing gets perfect 100% reflectance, right? So a little bit of the light is lost. So when I see myself in the mirror, all the light rays that hit me, they all hit the mirror. Some of them get absorbed. Not very many, granted, but then their light reflects back to me. So what I see myself is slightly darker than I really am. Now, if I were to try to do that infinite series, right? The two mirrors lined up and you poke your head in there and you see one reflection, the other reflection, back and forth, back and forth. Well, what's going to happen is every reflection gets that little bit darker. So can you really get infinite reflections? No, because you're losing a few percentage points of reflectance with every reflection. Well, that's the last thing to know with a plane mirror is you are slightly darker in the reflection than you are in real life. Again, not much. Probably a good mirror is getting 90 to 95% reflectance, but that means you're 5 to 10% darker in the mirror than you really are. So I don't know that any of you are those type who like to work on your tan necessarily, but if you were, you're not as tan as you think you are. I grew up in Florida, and I also grew up in a time when skin cancer was less of a big deal, and being tan and cool and beach boy looking was more cool. And so anyway, I tried to work on the tan just a little bit, and you know, I was one of those decent sort though, you know. So I had the tan from here down and from knee down, right, from working outside all the time in the summertime. But when I saw in the mirror, I wasn't really as dark as I thought I was. You have to look at yourself to see how dark you really are. Anyway, questions on plane mirror images. So 5 things to know, not in any particular order. First of all, images are, they're virtual. They appear to be behind the mirror. They are upright. Nothing's flipped over or anything weird like that. They are reversed, however, along the z-axis. And how can you undo the reversal? Have 2 mirrors, right? Right angle to each other works, or just front, back, as long as there's an even number of reflections. Unmagnified. What you see is the actual size things are. And darker, slightly darker. All right, we will hold off on the math for the next lesson on this, but the math is pretty straightforward because the angle of incidence equals the angle of reflection. You're going to find tomorrow that the math is pretty simple math with plane mirrors. For homework this evening, I need you to read over pages 277 to 285. I need you to read over pages 277 to 285. On page 290 Answer questions 3, 5, 6, 7, 10, 11, 13, and 15. A little longer assignment than usual today. 8 questions to answer. Page 290, questions 3, 5, 6, 7, 10, 11, 13, and 15. All right, have a wonderful rest of your day. When the bell rings, you'll be dismissed.